Alright, time for another DrivePhysics.com, debatephysics.com also, video presentation. Lesson 2, pretty much the Smalliverse argument, that there's only one universe, and it's not the one we're living in. Yeah, the real empty space and the real stuff, the actual elemental stuff, is a much smaller universe. Electrons, protons are really the universe. They're the things really in the empty space, and everything else is just a collection, a group of that stuff. And yes, it all looks opaque and solid, but we kind of know that there's a bunch of space inside things that don't look like there's any space in there, but there is a bunch of it. And that's where all the function starts. That's where it all happens. There's no action. There's no forces. There's no mechanism that's really interacting with us. It's all just these electrons and protons interacting with each other. And that creates all the electricity that's in our brains, that creates our consciousness, the whole thing. So it's all in the one universe, the very small one. And it's all based on this idea of something having energy, a component that's the essence of energy. We call often things that create that a force. So we have these words that we use, or symbols. Yeah. There. So energy is more or less the idea as a concept is that something possesses something that has energy. So there's an elemental motion in the universe. You can call it just a force bit. Okay, it's a little quanta, a little discrete bit of stuff that has energy. And the fact is, electrons, okay, and protons collect it. Now, there is a nuance to this in the sense that there's two kinds of force to go with these two kinds of elemental matter. But that's all there are. And if you want to make a neutron, you just put an electron and a proton together, actually. And that's your neutron. Okay. So those are the elemental parts. And the motion is basically them collecting this stuff. And when they have it, they move in the direction that that thing has as a motivator. So you can think of it as sisyphuses. Okay, a bunch of little tiny things that are pushers, and things that get pushed based on how many of these things they've collected in a direction. And they can't collect them in opposite directions, and so that would be the only rule that exists. So they could collect some going this way, okay, and then they could collect some going this way, and they're not in competition. So if they're separated by a dimension, there's no problem, but they can't do this opposing thing, because that causes a reflection. So they can never collect energy in two directions. They can only be either they have more going this way or they have more going that way, but they can't have an element of both. All right, and so that's how the energy is collected. And once the electrons and protons have it, okay, they cause atoms to move, and the atoms moving causes big objects like us to move. But it all starts here. So it's a three-dimensional space. I mean, I think plenty of people could understand that part of it. That the space is a real thing, okay, and it really does occupy space. I mean, there's distance between objects and even these elemental bits of energy. I guess we should just say F bit, okay? They're force bits. They're real, okay? Now, an interesting and convenient proof of this is the existence of gravity itself. So, in the case of a thing that has a lot of matter, it has a lot of electrons and protons. And the idea is when a bit of force hits an electron and causes it to move through the Earth, let's just say, let's say it could make the path, there was only a few of them and they could make the path all on their own, you can sort of understand that they would push, and then if something came in the opposite direction, a little force bit, that would cause this reflection thing, and this would cause this motion to change, and that this object could be going back and forth inside the earth, moving, and every time it moves, you know, these force bits are moving the speed of light. So the little elemental forces, gravity, magnetism, electricity, all this stuff, light, it all moves the speed of light. The speed of force is what it should be called. So it should be called the Smalliverse, and it should be called the speed of force, because it's all the forces have the same speed. And what's basically happening is when it's pushing one of these electrons and protons, it goes from going the speed of light very fast to something less than the speed of light. Okay, it won't be very slow, but it won't be nearly as fast. Maybe 1/100th of the speed, maybe 1/10 of the speed, something like that. So it's losing velocity while it's pushing. It's not getting where it was going. Okay, so you can sort of understand if there was a bunch of this force going into a body, and it's going to be delayed in how it's going to get to the other side, that the other side would always be feeling that delay, the absence of that force, because it's wasting time. It should have been here, and it's not going to be here because it's making matter move back and forth inside the earth. So the pressure this way and the pressure this way are creating just a bunch of wasted energy, in the sense that the matter is just going back and forth and back and forth, and that's consuming time. And so the earth ends up radiating less of the force in all directions because it's wasting energy in all directions. It's losing energy from the force because we're essentially reducing its speed. If the force bit pushing, okay, is going to move slower while it's pushing, you can understand that it should have been in a location, and it's not going to be there because it's going slower, and so then its average speed is in a sense lower, so it's losing some of its velocity. Okay, and Newton told us that mv, the mass times the velocity, is essentially a description of how much of this force you've collected. And so if you're going to reduce its velocity, essentially you're reducing its energy, essentially. And so that's why gravity exists, is because any material body that has electrons and protons in it, the electrons and protons are stuck in a universe that's going to keep pushing them in both directions. It's going to cause them to move. And they're not going to go anywhere, but they're going to move. And as they're moving, they're absorbing energy from the force. They're retarding the amount of energy the force has. So if you were measuring the energy of a force by saying, well, look, how far does it go in a second? So this is how far it should have been. Okay, you can sort of understand that if it's moving matter, the force bit might only get to here. So it's obviously got less energy because it's moving slower. So anytime energy, a force, interacts with matter, the energy is essentially stored in the motion of the matter now, not in the motion of the force. Alright, so we will erase and continue. Alright, I guess we will now talk some about how this force bits, okay, how they take form, alright, in what we commonly see. So if you're seeing a photon is essentially these force bits in an arrangement. So a photon isn't just one thing. It's not just a round object or a single discrete object. A photon is an arrangement of force, okay, that has a component, okay, a frequency, a period between, okay, arrival events, essentially. So these things are all traveling in the same direction. They have a distance between each other, that's their frequency, and they have another distance where they're separated from each other in space, okay, and that's their polarization. Okay, so the smaller the frequency, generally speaking, the smaller the polarization. So if this was red light, blue light would look something like, well, I guess I should make the bits themselves the same size. Blue light would look something like that. It would have less polarization and it would have a smaller period. And obviously, as you get gamma rays, they're very close together and very tightly spaced. So when they hit a surface, they'll hit some surface that'll be fairly large. Now, the key giveaway to that light isn't something that pops out of atoms. A single atom doesn't poof a photon. A single electron doesn't poof a photon. It's an arrangement, and it can be understood just by the frequency itself. The frequency of red light, for example, is some 1,000 atoms. Okay, so it's a huge distance between these objects compared to the surface they're hitting. So it really does take more than one atom being affected by the photon for the surface to react by creating electricity, which is just really a change in the atom's polarization. As you hit the atoms, you move the electrons and protons arrangement to each other, changes the shape of the atom essentially, and makes it magnetic for a moment, and that magnetism ends up creating electricity. So when the little force bits are in this arrangement, we call them a photon or light. But when they don't have this arrangement, when they don't have a frequency and they're just more chaotic, you could argue that's gravity. That's force that's always in the universe. There's pieces of photons, you could argue. You could just argue the pieces of photons flying through space all the time. And that's the stuff that's essentially going into the Earth and coming out retarded, okay, less effective. Now, magnetism is essentially the same idea, but everything, what needs to really be understood, okay, let me go back a little bit to the beginning, is that every material thing outside of the electrons and protons, so just any object, a brick in space, is basically interacting with this force. The brick itself produces nothing, okay? So, like a magnet even. A magnet doesn't produce anything. It's not sitting here with some sort of force that's generating, it's not a nuclear event, it's not a decay, it's not a radioactive element, it isn't creating rays of force. What it's doing is just reflecting the universe. Everything just reflects the universe. So the universe comes in, the force comes into things, and they just reflect it. Okay, they either absorb it for a minute and then shoot it out. And that's what the Earth is doing. The Earth is reflecting the energy in the universe, and the simple truth is it reflects, it absorbs, okay, more than it excretes. That's the time difference, the consumption of a little bit of the energy by reducing the speed of the force. And that little reduction in speed is what causes the gravity. So it just excretes a little less than what goes in. So you can understand a lot's going in, because just a little change in how much is going in creates the pretty substantial effect of gravity. But it's a gigantic Earth. The size of you compared to the Earth, is atom to apple kind of thing. It's a gigantic difference. So everything is just interacting. So if you have a wire, okay, and you're running electricity through it, what the wire's doing is not excreting some other kind of energy. The wire's sending electricity through the wire. The excretion, the magnetism that's flying out of the wire just has to do with the fact that the wire has changed its surface. It's changed how it reflects the universe. So before, where it could, like you could say, purple goes in and purple comes out, when the wire has been changed, purple goes in and bluish comes out one side and reddish comes out the other side. A pattern of red and blue. So it's just reflecting the universe differently. So a magnet isn't producing anything except an effect where purple goes in, a plain force goes in, and a more complex arrangement of the force comes out, meaning it's magnetic, but it's the same amount of energy. The magnet doesn't produce anything. It doesn't change any thing about the force. It just changes how it's going to get reflected. So that's an important part of this, is just to understand that everything is interacting with how they're reflecting the universe. So one object and another object see each other based on what they changed about what went in. Something went in and something else comes out, okay, a different pattern, and that's what they see, is just the reflections. Now, yeah, there are things that are actually decaying, okay, like when you have very heavy atomic nuclei, they fall apart because of their, under their own dynamics. They're obviously more complicated, and everything has to be more perfect for them to stay balanced, and they eventually break. And so the radioactive elements are excreting part of their energy that's stored in them by becoming simpler atoms. So by breaking into smaller and smaller atoms, they release a bunch of trapped vibrations, oscillations between electrons and protons as they dearrange the energies that's been stored between them. The tension is released, and so all these little bits fly out, this radiation, and in the form of either the force itself, little force bits fly out, or electrons and protons fly out, okay, with a momentum. So you have the beta, alpha, beta, and gamma type radiation, and it just means that you're breaking different pieces. Whole pieces of a chunk of an atom are the very elemental bits of the atom are what's breaking off and flying out. All right. Moving on. All right, so returning to the gravity argument, I think it's, you can understand that there are reasonable mechanical explanations for gravity, but there can always be catches to them. So the catch with the idea, okay, that there is a bunch of force in the universe and matter has to travel through that force. So there's little bits of force flying in all kinds of directions, and it can be understood that an electron flying through that force would end up hitting more force opposing its direction. So there's no way you could throw an electron in space and have the expectation that it'll keep going. And the irony is that's exactly what we find to be true. That if you try to throw electrons and protons, they have to keep being pushed. If you stop pushing them, they stop going, because they do drag to a halt, because they are plowing into, incidentally, more energy, okay, more force in the direction they're moving, and less force. Obviously the force bits behind them. If the electron was moving half the speed of light, you can understand that it would take twice as long for something to catch up to it, okay? Twice as long. So there's no relativity in any frame sense, space-time sense. There's just relativity in the sense that you can go relative speeds. And so a photon chasing an electron going half the speed of light will take twice as long to get to it, okay? It's just a fact. It has to catch up to it. So obviously there's less force pushing an electron than pushing against it, because the force heading for it, it's going to arrive twice as fast. So it's going to hit twice as many going this way as it's going to have pushing it this way. So obviously these collisions are going to slow it down, and it's going to end up stopping. And that's exactly what it does. So the experiments demonstrate we can't make a true electron gun and go into space and shoot electrons to some place 5 miles away or something. The electrons won't make it, okay? They will be dragged to a halt. And protons too. So this is also proven by, we have this atmosphere around the Earth, and these cosmic rays come in, and they're not in the form of electrons and protons. They're in the form of more complex arrangements of electrons and protons, nuclear bits, okay, pieces of a nucleus is what's really traveling. And so then there's something about combining electrons and protons that make it possible to create something that can be thrown into space and it keeps going. So inside of the nucleus there's bits that have this arrangement where they're more complicated but very simple. Okay, basically you could almost argue a hydrogen ion, you know, where you have a proton, an electron, and an electron. You might be able to understand that, say if you had this configuration, and let's make them the same size, because they probably are, because their charges are the same. Anyway, their charge density is the same. Alright, so I should make one of them hollow. Alright, there. So let's say this had a direction. Okay, you can sort of understand that the electrons don't like the electrons, but they do like the proton. And so, you know, they're okay as long as these two electrons can't see each other. And the argument would be is as the force hits, what it's really going to do is, if it's an electron force, that is a force that pushes electrons, it can hit this one. But if it's a proton force, okay, then it's going to be converted. When it goes through the electron, it's going to be converted from a proton force to an electron force. The electron force is inert to the proton, so only a proton force can push a proton, so it goes right through the proton and pops out a proton force again. And then when it gets to the second electron, it's now a proton force, and it just ends up converting it into electron force. So it's completely made, it's neutralized all the proton force, and none of the electron force can frankly get to this one, because this one interacts with it all. So any velocity this one has, momentum, it can't lose it. The only thing that can take this one's motion away is it has to actually interact with an electron force. And because this one's here, it can't. So it never sees any force that reduces its momentum. So every time this one slows down, forces this one to slow down, this one doesn't care, because it's inert to any pressure except the pressure it has between the protons. So it just keeps re-pushing this way. So no matter what happens here, this motor keeps pushing. And that's why this thing called a deuteron, okay, is what is a cosmic ray. So it comes in going very fast, and then it knocks atoms and pieces together, and that creates gamma rays and all X-rays and all kinds of other crap that ain't too good. But that's so they already have the evidence that drag is differential. That is, some pieces of the atomic structure are dragged to a halt, some pieces aren't. Alright, so they already have an explanation for why an argument about tired force, okay, the idea that light would get tired, or that the magnitude, the momentum of a force could be consumed or stored in motion, that theory still works, because the drag subject is defeatable, as it's not a real problem, because we actually observe that the tiniest bits are dragged. The force can't be dragged, because that's frankly just saying, if two force bits actually did hit each other, even if that were possible, all they'll do is replace, they'll just exchange. This one will end up going that way, and this one will end up going this way. Their interaction will be irrelevant. You'll still end up with the same outcome, just like if two things hit each other in a Newton's cradle. You end up with an outcome that's exactly what you would have had if they didn't hit each other. If they didn't hit each other, you'd have one thing going this way and one thing going that way, and if they hit each other, you're going to end up with the same outcome. So it's irrelevant whether they collide or not, because the collisions don't change anything. There's no difference in the outcome. Alright, well, I wasn't really going to get into the true nature of the force, but I figure it's worth throwing it in, just because it does make it easier to understand electricity and magnetism. So let's say the electrons and protons they're different, so we're just using color as a way of recognizing that there's a difference between these two things. Probably should have done it the other way around. Red should be the proton. Okay, I'm going to make this the electron. Okay. And the simple argument is there's two kinds of force that is flying through the universe, just like there's two kinds of these, what you could call dead objects, or dead force even. You could think of them as being force that did actually stop moving. Okay, now they're pushable, but whatever. It doesn't really matter. And so in the universe, there's two kinds of force. There's the proton force and the electron force. And the simple argument is if the red hits the red, it is absorbed. If there isn't already motion in the same direction, then it's absorbed. It sticks. But if there is already something stuck, let's say there's two of them stuck this way, and something hits this way, then this will just reflect, and this last one down here will reflect. So there's a balancing feature to it. But the key feature is that if an electron force hits, it just goes straight through and it just pops out a proton force. So the protons are always excreting red, proton force, because anything electron force that goes in gets converted to red. And then the electron's doing exactly the opposite, so it's just excreting, electron force. And now you can sort of understand the nature of charge, because this is exactly what Maxwell would have drawn in terms of how they behave. One of them has an energy, they're both moving out. Maxwell would have drawn the electron force going in and the proton force going out, but no, both forces are going out. And the simple argument is the red force can't hurt the electron, and the electron force can't do anything to the proton, can't move it. So that's why they move into each other. Is obviously all the electron force is still hitting the electron from out here, but it's not getting hit by any electron force in this direction. So it obviously moves towards the proton, and the proton moves towards the electron because of that circumstance. And obviously if I put another electron in here, you can understand that it's getting exclusively almost hit by electron force here, and all the proton force is turned into electron force, so it's almost doubled the amount of force here that affects it. And it still has, even though there's still a little bit, there's half as much purple force here. So you have twice as much here that you have here. And the red is obviously irrelevant, so, to the electrons. So there's nothing but more energy pushing them apart than energy pushing them into each other. There's more electron force on one side than there is on the other side. In this case, there's more on this side than there is this side. And obviously, the closer they get to each other, this force just keeps bouncing back and forth because the motion is against it, so it's all reflecting. And so if it's moving towards, it's going to reflect everything. And so now you're really multiplying. So that's why the electron force gets stronger and stronger and stronger the closer you get. Same with magnets. The attraction and the repulsion. So that's the nature of charge. And then magnetism is really about atoms. And what happens to the atoms is they essentially polarize. So they have an arrangement of electrons and the positive nucleus. And all you're really doing is compressing them in one direction or compressing them in another direction, and you're just changing their polarity. That is, you're making them more magnetic, in terms of they'll have a side that's decidedly north, and then they'll have places where they're decidedly south. And so they can have more than one pole, but the fact is that you're changing their shape by moving the electrons in and out. You change how much red can be seen from the external world and how much purple or blue is seen from the external world. And by changing those relationships, that just turns them into magnets that you can see, that a magnet could see, because they now can see the pattern. They can see that the pattern of red and purple matches their pattern of red and purple, and therefore they'll repel each other, and when they're misaligned, will attract each other. So it creates a mechanism to understand all that. So yes, there's just two kinds of matter, elementally, The universe is just made out of two kinds of matter, electrons and protons. There aren't anything else. The 400 other standard model thingies, taus and muons and gluons and all that crap, those are just the speeds that you can move electrons at. So if you move an electron at a certain speed, they'll call that a new particle. But no, it's just an electron moving a speed. And you can also move combinations of electrons. You can move hydrogen atoms at different speeds, and they'll call that, say, a muon or something. Anyway, but that's all there. There's just these two kinds of matter, and there's these two kinds of force, and there's only the two kinds of interaction, essentially, the reflection or the conversion from blue to red or red to blue. So that's about all you have running the whole universe, is two force bits, two matter bits, and two kinds of interaction. 2 plus 2 plus 2 physics.
Fascinating. Really fascinating. In fact, the most fascinating thing I've ever heard.